Now it's time to move on for the marginal probability distribution. So marginal probability distribution is a probability distribution that gives the probability of an event or set of events occurring. So before uh, we have seen the joint probability distribution where you can work on two random variables or two or more random variables at a time. Okay, it establishes a relationship between the two or more random variables. So that's what is your joint probability distribution. Now we want to do more. It's not just two or more. We want a set of events. We want to do a set of events. So then comes the marginal probability distribution. So marginal probability distribution is a probability distribution that gives the relationship, that gives the probability of an event or set of events occurring regardless of the values of the other variables. So, in the context of computer vision and natural language processing (NLP), marginal probability distribution is used to compute the probability of a particular feature or a word occurring, regardless of the values of the other features or words. So in computer vision, suppose we have a joint probability distribution of two random variables. We have taken this example in a previous case. We can follow up. So same example. So in computer vision, suppose we have a joint probability distribution of two random variables, capital X and capital Y represents the pixel intensity, and capital Y represents the object labels. The marginal probability now comes to the marginal probability. Marginal probability distribution. So the marginal probability uh, distribution of X is the probability distribution of capital X regardless of the value of Y. So it's computed by, so that's what is the marginal. You made it marginal from there to here. So I'm repeating, when this is your joint probability distribution, the X and Y, in that case the marginal probability distribution, so the marginal probability distribution of X, the marginal probability distribution of X is the probability distribution of capital X regardless of the values of capital Y. Value of capital Y. That's what is your marginal probability. So regardless of value of capital Y. So it's computed by summing the joint probabilities over all possible values of Y. This is how we calculate. So P of capital X is equals to small x, so which is equals to summation of all possible values of small y of P of, obviously, joint probability of capital X and capital Y. And this is how we calculate the marginal probability distribution of capital X. Okay, so here the marginal probability distribution of capital X gives us the probability of a particular pixel intensity occurring in an image regardless of the object label. So marginal probability, it could be PMF or PDF of one random variable accounting for all possibilities of the other random variable. So for discrete random variable, probability of capital X, let's take probability of capital X will become, as I have told you, the probability of the probability, marginal probability distribution of capital X is equal to the probability distribution of capital X regardless of the values of Y, capital Y. So it's computed by summing the joint probability. You see that? Summing the joint probabilities uh, probabilities over all possible values of Y. So sigma Y P of capital X comma capital Y is equals to Y. That's what. Or else, if you want it marginal probability distribution for Y, then P of capital Y is equals to sigma X, P of capital X is equals to small x comma capital Y. So this is how you calculate the marginal probability distribution for respective random variable regardless of other variable which is a part of joint probability distribution. So for discrete random variable, it is the sum of the PMF table along the rows or columns. And this is what your, yeah. So this is where you can see. So capital X here, capital Y. These are the two random variables. Capital X is one random variable. Capital Y is one random variable. Now for discrete random variable, so it's the sum of the PMF table along the rows or columns. That's what. So probability of capital X is nothing but sum over rows. Sum over the rows, sum over the rows, like this, sum over all the rows. If P of Y, marginal probability of capital Y is sum over columns, you do that like this, because as it is X, it will take up all the rows. As it is a Y, it will take up all the columns. So that's what we did. You can see P of capital X is nothing but summing up all the rows. See that? Y is equals to Y. When it comes to the probability of Y, which is summing up all the columns, that's what we did here. So the definition is also applied for two sets of random variables, and marginal of one set of random variables is obtained by summing over all possibilities of the second set of random variables. So similarly for continuous random variables, as it is continuous, I need to go for the integration. Here I don't need double integration, I need a simple single integration, but the integration limits changes and the integration will done by other variables. So for to calculate the P of capital X, it is the limits are given by the Y, and then P of capital X comma capital Y is equals to Y, and it will be integrated with respect to the dy. When you want to calculate the probability of capital Y, then it will be integrated with respect to the dx, and the limits are also given by x. So that's what for continuous random variables. So similarly, if you take an example for NLP, natural language processing, we have a joint probability. Let's take the joint probability first. So then it would be much clear. So let me put NLP. So let's take a joint probability distribution, because these are all works in hand with each other. So we have a joint probability distribution of two random variables, capital X and capital Y, capital X and capital Y, where X represents the words in a sentence, and Y represents Y represents the sentiment labels, because sentiment analysis, sentiment labels. Y represents the sentiment label. Now the marginal probability. Now the marginal probability of X. We show it as P of capital X. The marginal probability of X, which is P of capital X, is equal to sigma of y p of x comma capital Y is equals to y. We have shown that equation. It's pretty difficult to type here to bring that summation value. So the marginal probability of y, so and that's how we compute the probability of x. So which means the marginal probability distribution of x is the probability distribution of x regardless of the value of y. So it's computed by summing the joint probabilities over all possible values of y. So the marginal probability distribution of x gives us the probability of a particular word occurring in a sentence. So at the end in words, what does the marginal probability of x gives? The marginal probability of x gives us the probability of a particular word occurring in occurring in a sentence regardless of the sentiment label. So I'm repeating the marginal because it's marginized to the random variable x. So the marginal probability distribution of x gives us the probability of a particular word occurring in a sentence regardless of the sentiment label. But when it comes to joint probability, it will give you the joint probability. When it comes to the marginal probability, irrespective of the sentiment labels, it will give the probability of respective word occurring. That's what is your marginal probability in a nutshell. So the marginal probability distribution is a useful tool in both computer vision and NLP for feature selection. So dimensionality reduction and other tasks that involve analyzing the probability distribution of a particular feature or variable. By computing the marginal probability distribution, we can gain insights into the probability of individual features occurring and their impact on the overall probability distribution.